Hey guys, today we're going to be looking at conditional probability and tree diagrams in order to model those situations. So a quick thing about our conditional probability is that it's where the outcome of the first event or one event impacts the probability of the second event. Another way to describe this is the word dependent. Dependent, or the result of one is dependent on the other. Alright, so we can quickly talk about independence while we're here, which is where they do not affect each other, and it changes things a little bit later down the track when we get to our conditional probability formula. But for now, let's look at an example of where conditional probability fits. Okay. We have a box of batteries used for calculators, and they originally had 24 new batteries in it. Unfortunately, 10 batteries were put into a box when a class set of calculators were changed. Who does that? So, now they've taken out 10 and replaced them with 10 flat ones. We've got a total of 24. Now, as we take the batteries out, the total changes, and the result changes how many of each we have. Okay, so if we take a new one out, then there's going to be less new, and if we take a flat one out, there's going to be less flat, changing the probability overall. So we can quickly calculate a couple of these. So if the first battery was flat, what is the probability that the next one will also be flat? So we're only worried about the probability of the second battery. Okay, so we're not talking about what's the probability of drawing a flat battery and then another flat one. We're talking about just the next one. So how many batteries are there after we've already taken out the first battery? Well, there was 24, so now there's 23. And the first one was flat, leaving 9 flat batteries left. So 9 out of 23 batteries. Let's try it a couple more times. If the first 2 batteries taken out were okay, what is the probability that the next one will be okay? Again, we're talking about the next one. So the results of the first 2 have already happened. We're just talking about a particular thing. Oh, the third battery. So we can write this as the probability that the third is okay, given that the first 2 are okay. Now, if the first 2 are okay, we had 14. So there are only 12 okay batteries left. There were 24. So 12 out of 22 is the probability of getting an okay battery after 2 have already been drawn. Now this would be different if we drew a flat battery instead of an okay battery, because then there would still be, well, there would be more okay batteries in the box. If the first 5 taken out were flat, what is the probability that the next one will also be flat? So, looking at the probability of the 6th one being flat, given the first 5 are flat. Well, we've taken out 5, so there's 19 batteries left in the box, and there were 10. If we've taken out 5, there's 5 flat batteries left. This guy's got some bad luck to get 5 flat all in a row. Okay. So, tree diagrams can be useful to model the changes at each step. Now, with tree diagrams, we've got some properties that are going to be useful that we'll use along the way. Okay. The probability of each outcome is each branch along that path multiplied together. I'll show you in a moment. The outcome at the end of each tree diagram, or the end of each branches, is mutually exclusive, which means we can add them along the way without worrying about the crossover of the events, because there isn't a crossover in mutually exclusive events. Each set of branches should total to 1. And again, we'll show that but that's because all of the outcomes should be demonstrated at the tree diagrams. It should be not this and not null. So let's go through an example. Hopefully it makes a bit more sense. So we have a bag of 5 marbles, 3 green and 2 red. So depending on what we draw first is going to change what happens. We're supposed to be doing this with our replacement. And we're actually drawing 2 marbles. So there's 2 outcomes. On the first marble we can either get green or we can get red. And then if we get a green, how does that impact the probabilities of the next one? Start with the first marble because that's going to change what we do here. 3 out of those 5 marbles to begin with are green, and 2 out of the 5 marbles are red. If we draw a green marble, then there's only going to be 2 out of 4 green left there, and 2 out of 4 red. Go for the other branch. If we take out a red marble, then we're going to have 1 less. We're going to have 1 out of 4 red marbles, but the green hasn't changed. 3 out of 4. Notice that 3 out of 5 and 2 out of 5 add together to make a total probability of 1. 2 quarters and 2 quarters, probability of 1. 3 quarters and 1 quarter, again, probability of 1. So this is what I meant by each set of branches totals to 1. At the end of each branch, probability of 2 green is going to be equal to, I really should have done the first probability. Let's try that again. 3/5 times by 2 quarters, or 6 out of 20. I don't bother to simplify along the way because it's going to make our calculations later a little bit easier. So that's what I meant by multiplying each branch along that path, 3/5, 2 quarters, 3/5, 2 quarters to get your 2 green. And we'll get to the mutually exclusive on the different colors. So, probability that both are red. Well, we're following this set of pathways here. So I've got 2/5 times by a quarter, making it 3/20. With our next example here, probability of different colors, we can have a green-red, or we can have the red and green. Both situations result in different colors, so we're going to need to add them. And we can do this because each branch of our tree diagram happens, they can't happen simultaneously, they're mutually exclusive to one another. So we're going to add probability of green, then red. So getting a green first is 3/5 times by 2 quarters for the red. We're going to add probability of red. Getting a red first is 2/5 and times by the green, which is 3 quarters. And we should get 12/20 as our final answer. Last example for this video, we're going to be looking at probability of being dealt 3 of a kind as your first 3 cards. So this might mean ace, 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 king, 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 6, 6, 6. We don't want 2, 3, and 5, or 2 2s and a 3. We're looking for 3 of a kind. So we're going to split this into three parts. We've got the probability of the first card. Now, because it doesn't matter at this stage what card we get, this is 52 out of 52. Once we have our first card, then we need to consider what's changing here. We want the probability of it being the same kind with the first card being drawn. Now there's 4 of each kind of card there. There's 4 jacks, there's 4 queens, there's 4 fours. So if we've already taken one, there's going to be 3 left over, and there are 51 cards still left. If we've taken 2 of them out, and we want to know the probability of it being the same kind, there's only 2 out of 50 cards that they still have it. So the probability of 3 of a kind is these all multiplied by one another. We don't always need to use the tree diagrams, but if you were to draw one, this would be the relevant part. We've drawn our first card, and then we talk about the probability of the first one, of the next one matching, 3 out of 51, and then the next branch would be looking at the outcome for matching, is 2 out of 50. There's obviously another set of branches out here that we could talk about where they don't match, or not a match. So this one would be 48 out of 50. The rest, because it's not. If we type this into our calculator, we should get 1 out of 425, which we could convert to a percentage if we wanted to. Hopefully that helps. Let me know if you've got any questions.